Hello everyone. I'm Sai Venkatrakrishnan, a PhD scholar in the Department of Computer Science and Engineering. This is a weekly live session for the NPTEL course Operating Systems Fundamentals. Um, the agenda is as follows. We will be discussing around 10 questions, which were given in the previous offering of the same NPTEL course. We will be discussing those 10 questions and we will be seeing how to approach the question and the solutions for that question. So this would help you to better understand the lectures, and also it would help you to answer the current assignment 3 questions that you will be uh, answering, that you will be submitting for this week 3 for this NPTEL course. So let's move on. So the first question that we will be discussing is as follows. A program becomes a process when which of the following options is correct? Option A is it the program is stored on a disk as an executable. Option B, the executable file of the program is loaded onto the memory. Option C, the process replaces the program which was stored on the disk. Option D, none of the above. Okay, so let me just introduce myself for the one who joined new. Hello, I'm Sai Venkatrakrishnan. So, we are starting the live session now. The agenda is we will be discussing some questions, and we will see the solutions so that you better understand the weekly lectures and you will be able to answer the current assignment questions in the current offering of the NPTEL course. Okay. So the first question is as follows: a program becomes a process when which of the following options are correct? Is it when the program is stored on a disk as an executable, or option B, is it the executable file is loaded onto the memory, or option C, the process replaces the program which was stored on the disk? Any guess which one is the correct answer? A, B, C, or D? When does the program become a process? Okay, so let's go through the options again. So first we'll understand the question. What's a so there are two concepts being mentioned in this question. One is the concept of a program, okay, and the second is the concept of a process. So what is a program first of all? So whatever you write in a .c file, right, in main, and say some printf, something you will be writing. So this whole .c file is the program, and this will be stored in your disk. So this is your program which is stored on the disk. Now when does this program become a process? So if you had gone through the lectures, your process is something, so when this program is being executed, it becomes a process. So the disk is actually a type of an IO memory, like a secondary memory. And in a system, any executable or something which has to be loaded, and the CPU has to execute. So your load, store instruction, everything acts with respect to your main memory. That's the RAM. So whenever your program is loaded from the disk into the main memory, it becomes a process. And a process is nothing but it's an active entity, and this program would be given some memory area within the memory space within your main memory. So it will be given some memory space, and also some the scheduler and all those things will take care when this process should be executed and all those things. So all this will occur only when the program is loaded into the main memory, and it's turned into a process. So the program as just as such, which is stored on the disk, is a passive entity, and it just contains the set of instructions. And if you have any say global variable like int uh, g equal to 0, all these things would be stored in the as part of your program on the disk. But when it's loaded into the memory, some memory space would be allocated in the main memory. Some structures, the page tables, etc. Many meta information, metadata would be allocated to handle that process. And say this hello.c is stored in an executable hello, and in your command line you can run it like dot slash hello. So this dot slash hello is nothing but it will create a process by loading the program hello into the main memory. And you can very well open multiple terminals like this. Multiple terminals you can open, and you can run the same dot slash hello like 100 times also separately, uh, simultaneously also. Each time what will happen, the same hello program, this hello program would be loaded into the main memory and it would execute. So there will be somewhat say 100 copies of the same hello program, and but each will be in a different process. So that's the mapping between a program and a process, right? So out of these options, um, the program becomes a process when the executable file of the program is loaded into the memory. So the executable file is nothing but this hello dot slash hello, right? The compiled program. So that's the executable. So the correct option in this case is option B. So the remaining options are wrong. The process replaces the program which was stored on the disk, or option A, the program which is stored on the disk is the process. So those are all wrong options. Option B is the correct option. Okay. Any doubt in this question? The concept of a program and a process. Okay. So in that case, let's move on to the second question. Okay. So the second question is as follows. It's fill in the blanks. Program is a dash uh, quantity and process is a dash quantity. So whether it's an active or passive quantity or passive active, or the option C, program is a passive and process is also a passive quantity, or option D, whether it's an active entity, the program and the process are active entities both. So any idea which one of the following are the correct options? Option A, B, C or D, which one is the correct one? Any guesses? You can either unmute yourself and speak, or you can put the message in your chat box also. Okay. So first of all, let's understand what they mean by an active entity or passive entity. So when they mean an active, okay, B, program is a passive and process is an active. Okay, yeah, that's the correct answer, Satya Prakash. Yes. So let me just explain it. So the program is nothing but it's the passive. So by passive, what it means is it's just stored on the disk. That's it. Statically, it's just like static. It does not do anything. If you want to execute a program, it should be loaded into the main memory, and the process would be created with respect to that program. It would be assigned a PID, some page table, some process control block structures, everything would be assigned. So all this is part of a process only, and then your instruction counter would be loaded, the program counter, the registers would be set, all those things. So all those things are would actually happen only when the program is loaded into memory and turns into the process entity. So in that scenario, the program is the passive entity and the process is the active entity. So option B is correct, as you mentioned. The other options A, B, C and D, A, C and D are wrong. Option B is the correct option. Okay. So let's move on to the third question. Okay. A process structure may contain which of the following? Option A, whether it will contain a heap, uh, or option B, excuse me. Option A, whether it will contain the heap memory. So whenever you do a malloc, right? Malloc in C or a free function. So all these things interact with your heap. So whether it will contain the heap or whether it will contain the program stack or it will contain the data section or it will contain all of the above. Any guesses which one the process structure may contain? So when the program is loaded into main memory as a process, say process P1, what all will be within this process? So of course, whatever your instructions, right, the main function, everything, so all that will be in your text section or the code section. So what else would be present in your process structure? Whether it's the heap or the stack or data section or all of the above. Any guesses? Option B. Okay. So you mentioned option B. Okay. So let's first see what each things are. So what I'll do, I'll write a sample program and let's see what all will be there in that program. Okay. So um, okay. So let this be like int uh, glb equal to 1, then int main, okay, and then int star a equal to malloc, okay, and then int b equal to 5, okay. Then I'm freeing this a, so this malloc is for say some 10 bytes or something. Then I'm freeing this a and I'm then returning 0. So this is my main program, and this is the full program. It contains one global variable. It contains a main function. Some pointer is being malloced, and I'm storing some integer in one variable b, and I'm freeing that a. So this is just like a dummy function. Now within this function, what all will be stored in the heap? What would be stored in the data section? And what would be stored in the stack, program stack? Okay, so let's see. One, we'll start from the top. The first thing is we'll be seeing is this int globe, glb. So this glb is a global variable, and it should be accessed throughout the program from any function, from anywhere it should be accessed, and it is not being assigned via some call to malloc or something like that. So where this will be stored is it will be stored in the data section. So this glb equal to 1 would be stored in your data section. Okay. Now this we have seen this glb. Now coming to the main function. So all the instructions within the main function as such would be stored in your code section. So the main function, all instructions would be stored in your code section. Now within the main function, if you notice, I am using the malloc function to create a memory of 10 bytes. Okay, and then I'm assigning some value of value 5 to a variable called b. Now where will this malloc region, 10 bytes malloc region, I should allocate from somewhere. So where will this 10 bytes reside? So this malloc is a dynamically allocated memory. So this malloc could be allocated from the heap region. So whatever value this pointer A has, this malloc region 10 bytes, this should be present in your heap. The 10 bytes region would be malloc from the heap and it will be given to A. Now this value 5 we are assigning to B, right? This is something which is local to your function, main function. So that will be stored in the program stack, because any temporary variables or local variables within your function, those will be stored in the program stack. Okay, and also apart from b equal to 5, what else would be stored in that program stack? There will be this pointer a. So this a is nothing but a pointer which is pointing to the heap 10 bytes. So whatever you had malloc, right, this malloc will return some pointer, say 0x80. So that 0x, excuse me, so that 0x80 would be stored over here in the stack. So in this program itself, if you notice, one variable's value is stored in the data section, that is the GLB variable. The other data, the local variables within a function A and B would stored in the program stack. The whole function as such, all the instructions, the call to malloc, everything is stored in the code section. And the malloc region, whatever this pointer A is pointing to, that is allocated in your heap. So all this together makes your process. Okay, so the question, so the question, a process structure may contain which of the following, whether a heap, a process stack, or a data section, or all of the above. Out of these three, a process may contain all of the above. Option D is the correct option. Notice the question properly. They have asked whether it would contain. So see, they have asked whether it may contain only. So why are they asking a process? Why aren't they asking like a process structure must contain a heap, a process stack data? Why aren't they asking in such a way? Why are they asking it as like may contain is because if you don't have this, let me use some other color. If you don't have this malloc over here, this malloc call, we are removing this instar a equal to malloc, then what would happen is you and also we assume that there is no call to malloc, no malloc itself in your program anywhere in the process. Okay, malloc is not being called at all. In that case, what happens is the heap section as such won't be allocated in your process. That memory space would be there, but it won't be assigned as a heap and no memory would be allocated from that process. So in that case, there won't be a heap section itself within the process, no dynamically allocated memory. But the program stack and um, and the data section, for sure it must be present in your um, process. Mostly it will be present. So that's why they have asked a question as what all things a process structure may contain, if at all it has to contain. So we find an example where it will contain all the above. So there is the globe, variable, dynamically allocated value and the temporary value, all these things. So it will contain all of the above in this scenario. So the correct option is option D. If they had changed the question to something like a process structure should contain what following is, mostly it should contain for sure the code section. It should contain the code section, and it should contain um, a stack for sure, a process stack. And third, it may or might not contain a data section. Mostly it should contain a data section. So these three are for sure the programs should contain. Most of the programs will contain this. At least the code section, it should be within the process, and the stack also should be within the process. So this is what the stack is also not mainly required, but the code section as such, the process structure should contain for sure. So this is what is the question. If they change this may to should contain, right, the answer would vary. So it is uh, necessary that you read the question properly and understand whether they ask process structure may contain or it should contain. Based on that question the answer changes. So any doubts in the following thing? Okay, right. Any doubts till now? So if no doubts in that sense, we can continue with the fourth question. If you have any doubts, you can unmute yourself and speak up, or you can put it in the chat window also. Yeah. So the question 4 is as follows. When the process right. So when the process is waiting to be assigned to a processor, the process state is called whether the process is in a new state, running state, waiting state, or a ready state. When a process is waiting to be assigned to a processor, whether it's in a new state, running state, waiting state, or ready state. Any guesses? Don't worry if your guess is wrong or right, you won't be judged. So just you can guess, and if you know the answer very well, you can. Okay, so some have mentioned D. Any other choice? Option D, or which one of the following state the process would be when it is waiting to be assigned to a processor? In a new state, running state, waiting, or ready state? So one has told it's option D, ready state. So what's first? Let's understand the various states a process can be in. So when a process is created, it's obviously in the new state. It's created. So it's created in the sense the process control block structure, all the file information, etc. So all those things would be IO devices. Everything would be set up, would be stored in this process control block structure, and stack, everything would be all the process control block structure as such would be created. So this PCB structure would contain all the information. So that's the new state. Once that is ready and the process is ready to be executed, right? So in that case, it will go to the ready state. And once I have a processor on which this process can be executed, I have a free processor. In that scenario, at that time, it will move from the ready state to the running state. And suppose, say, while executing the process, in between I get a IO operation or some interrupt occurs or something, and the processor cannot continue executing the program, cannot continue executing the process, and the processor has to handle that interrupt, or the process has to uh, wait for some IO operation to occur, or to say you have a scanf or something. In that case, what happens is the process moves into a waiting state. Okay, and once the interrupt is finished and now the processor can take some process and continue executing it, or the IO operation is finished, say whatever you are expecting from the keyboard, the scanf operation, those things, that information is available to the process. In that case, what happens, the processor will signal the process, and then it will continue executing that stopped process. So from the waiting state it will go to the running state, right? So it will continue running, and it can alternate between running, waiting, and all these states. And say for example, if the um, uh, it, say like your IO example, once this process uh, finishes execution, say there is this exit call or something. In that case, what happens, from the running state, it will directly go to the terminated state. So these are all the process states that a process can be in during its lifetime in the system when it's loaded into memory initially. So the question here is, when the process is waiting to be assigned to a processor, the process state is called which one of the following? So the answer is, based on the lectures and you would have gone, it's option D, that is ready state. So whoever had mentioned option D, it's the correct option. Okay, so that's the ready state. Any questions? Any doubts in this question? If not, let's move on to the fifth question. So the fifth question is as follows: a process control block contains information. Okay, so one second. So in the previous thing I had mentioned, from waiting state it will go to the running state. That's a small uh, correction. Uh, Say you have multiple processes running. Um, Say you have a P1, P2, P3, and suppose currently P1 is in the running state, and from running state it went to waiting state because it was waiting for some IO operation. Now seeing this, the processor, what it will do is it will take process P2 which is in the ready state, and it will keep process P2 in the running state. And suppose assume that process P2 is still running, but process P1, say it is waiting for some scan of input operation, and that IO operation is over for process P2. In that case, from waiting, process P1 won't directly jump to running state because there is already a process P2 that is executing, that is being executed by the processor, and it is in the running state, right? So in that case, what will happen is process P1 from the waiting state, it will go to the ready state. And now what happens is, suppose say process P2 now does some IO operation and now it is in the waiting state. In that case, now what the processor will do is it will check, okay, so I was executing process P2, it's now in the waiting state. What other processes I can execute? The processor will check. In that case, when it checks the ready queue, it will see that process P1 is in the ready state. In that case, it will take the process P1 and start executing it. So process P1 will be in the running state. So this is how the thing would work actually. So from waiting state it will go to the ready state, and then it will come to the running state once the scheduler, the kernel scheduler, those things pick up that process and give it to the processor for execution, right? So that's a small clarification I missed. Any doubts in this question? Question 4. Okay. Uh, in that case, we will move on to the fifth question. A process control block contains information associated with each process. So match the following information column with the relevant process column. So it's as follows, like I'll just zoom in, listen. So you are given this table. What you should do is you should match on the left hand side is the type of the information, say IO status information and all those things. And in the second column is the actual information that is being stored. Now you should match the actual information to the type of information it is associated with, right? So whether there are multiple options, so any guesses which matching is correct? Option A, B, C, or D. So let us go one by one. Um, Starting with memory management information. Which one of these following? P, Q, R, S, right? P, Q, R, S. These are the, so memory management information. What associates with this memory management information? We'll see one. Option A, Satya Prakash tells, okay. We will see one by one, right? So memory management information, out of these, what it contains. So if you see priorities, no, that's not related to memory management. If you see list of open files, no, that's not related to memory. Your memory management is for the virtual memory that is allocated to the process. Clock time elapsed, no, it's not related. So in that case, the queue row, memory allocated to a process. So this is what relates to the memory management information. So this is one. So memory management one maps to queue. Okay. Now in the same way, we will see for the IO status information. So IO status information is nothing but what all IO files a process can use. Say your process P1, when you are executing, you will have some function like f open, f close, something like that. So whenever you do f open, right, in your process control block PCB structure, the say you are opening some file um, hello.txt for reading. So this file would be given some identifier, say some integer identifier, say 3 or 4, something like that, and this would be added to the list of files that the process is currently being used, right? So the IO status information contains all these things. So by default, your display device, that is standard output, your keyboard standard input, all these things are also part of the IO information that is stored in the PCB. So the IO status information points to the list of open files, and if you notice, this R column points to this IO status information. So for R, it is, excuse me, option 2, right? So this is the mapping. So we have finished 1, 2, okay. Now for accounting information, right? So accounting is nothing but this accounting is like a miscellaneous thing, but it should always be there for a process. It's always so what all it's being using till now, all those things it has to be accounted for. So this accounting information is somewhat a bit tricky. But what you can do is, if you notice option 4, CPU scheduling information, right? CPU scheduling information, the main thing is for this you need priorities. So say you have multiple processes such as P1, P2, P3, right? So in that case, which one of the following process has to be executed first? Assume all three are in the ready state, all the three processes. So in that case, which one should be given priority? So that priority number, it will be uh, based on, say, P1 was uh, started say 15 minutes back, P2 only 10 minutes back, and P3 is 5 minutes back. Now my priority can be, okay, whichever process came, um whichever process came first, let's execute that process. So in that case, the priority number should be such that P1 should have a higher priority compared to P2 and P3, right? So in that case, the priority number of P1 should be higher than P2 and P3, and the CPU, the kernel would look at that priority number and choose P1 and execute that process P1. So in that case, the CPU scheduling information should have access to these priorities. So this information is part of the CPU scheduling information. So in that case, um, uh, option PQ. So CPU scheduling information is matched to P. So the remaining thing is nothing but for accounting information. It should be yes. So if you notice, accounting information is nothing but if it's matched to S, that is a clock time elapsed since start. So it's just accounting for how much a process is being, how much time the process is being active, and all those things. That's what accounting information is all about. You can use this information any way you want, but this is like a standard information that for all processes it has to be maintained, uh, this accounting information and all these things. So so P to right, so 1 is Q, 2 to R, 3 to S, and 4 to P. So in the comments, Satya Prakash had mentioned option A. That's the correct option, right? That's what we have mentioned. The other matchings are all wrong. So option A is the correct option for this question. Any doubts in this? Right. So in that case, we will move on to the sixth question. A process does not give up the CPU under which of the following conditions? After a specified amount of time has elapsed, option B on a IO request, option C when the stack memory is full, or option D none of the above. So understand the question. They are not asking when will the process give up the CPU, but they are asking when does not the process give up the CPU. Any guesses which one of the following options would be correct? Option A, B, C, or D? We will go through one by one the options. So if it's just like one process, say P1, P1 is executing means on the CPU, no problem, because that's the only process and it will keep on executing. Suppose say another process P2 is in the ready state. Now it wants to get executed, and this P1 has been executing for say 10, uh, 10 minutes continuously, and P2 is not getting chance at all to get executed. This is wrong. So the CPU is kind of like biased, you can say, right? So to avoid this condition, if multiple processes are waiting to be executed, what the CPU ensures that each of the processes will get somewhat equal amount of time to get to being executed on the system, each of the processes. So P1, P2, P3 all would get the somewhat same amount of time. So in like a round robin fashion or some fashion, the CPU, the kernel should ensure each of the process that is in the ready state waiting to be executed by the processor should be should get a chance to execute, and the processor has to be allocated to that process. So in that case, what the easy way is, it will ensure that after some for some period of time, P1 for say like every 5 minutes, once the 5 minutes has elapsed, it will stop executing P1. It will take P2, and now after this 5 minutes, it will stop P2 and it will take P3. So like that, every 5 minutes, it will keep on switching the process. So in that case, what happens? For some fixed duration of time only the process can execute, and then later it should give away its control over the system to some other process. So here they had asked not give up the CPU under which of the following. So this option A condition as such is a proper condition under which the process gives up the CPU. So this is not the correct answer, right? Let's see option B on an IO request. So you say suppose take the other the condition like only P1 is there, process P1, right? And CPU is there. It's running on the CPU. It's in the running state. And suppose say you have a scanf, right? In that case, what happens? The P1 should wait for the IO device from the keyboard to give some information to the process. So that waiting time, the process P1 would be in the waiting state only. So in that case, process P1 is in the waiting state, and it is not running on the processor, the CPU. So in that case, the P1 is in the waiting state and not in the running state. So the IO request is also a valid condition under which the process gives up the control over the processor. It's in the waiting state. So option B is also a valid option only. The question is asking for an invalid option which does not allow the option where a process does not need to give up the CPU. So let's see option C. So option C is when the stack memory is full. So when the stack memory is full, so if you notice, for every process structure there will be a code section, um, data section, heap, stack. So these four sections should be there. So the stack section is nothing but say you are calling multiple functions like F1 is calling F2, F2 is calling F3 function within your hello program, right? Assume this. Now for what happens is during each of these function it will have multiple local variables. So within your function there will be say a local array of say array of 10,000 integers, and you are sorting that integers in ascending order. So for each of these things, what happens? Your stack memory would be used up. So 10,000 integers means into 4, so 40,000 bytes would be used up. So assume like this specific function is called multiple times, and it is similar to this function. You have many types of function, and it also everything takes up so much of memory. By default, whenever the process first gets started up, for the stack it will allocate by default based on your system parameters one page. It will allocate, so one page is nothing but uh, 4000 one page, 4 KB, right? 4096, I guess. Yeah, 4096 bytes. I might be wrong in this. 4 4 KB. So some size should be allocated. So this page granularity, okay. Don't worry about the size things. So assume like it's allocated only 1000 kilobytes, okay. And assume while the program is executing, all these arrays, whatever is being executed, it uses up all this 1000 KB of the stack. Now again it is calling some other function, and when it is calling some other function f2, okay, this function is calling f2, and here again I want to declare an array b of 1000 integers. In that case, what will happen? All my 1000 KB is used up, and now again I want to allocate this 1000 integers. In that case, the program won't stop, because in your modern systems, right, you will have much of main memory. It will be the available space would be like 2 power 48 uh, or 48 bits. So that is more than 1000 GB actually. The available virtual space. Okay, the actual physical space might be low. In your main memory, it will be 16 GB or something. But the virtual space as such should be greater in a 64-bit process. Even if your memory space is very low, you will have your secondary memory. So what you can do is, you can swap out some part of the main memory into the disk, and the remaining portion you can free up such that this 1000 integers pointing to array B can be allocated in that free space. So going out of memory space or something is should be handled by the operating system in a smooth fashion, right? Only when it goes beyond the virtual space itself, it will lead to an error. It won't lead to something like a interrupt or something. It's a memory error, segmentation fault in that case. Usually, when the stack is used up fully, some other memory space would be assigned, and the stack size would be increased. It will be doubled to 2000 KB or something. So this option C, when the stack memory is full, the process would give up the CPU is wrong. It won't give up the CPU. So in that case, option C is the correct option. So this is a condition where a process won't give up the CPU when this condition occurs. So any doubts in this question? Right. If you have any doubts, you can unmute yourself, or you can post it in the chat message also. Not an issue. So we will move on to the seventh question. Right. The set of processes waiting for an I/O device is classified as is. We can rephrase this question. It's classified, or it's assigned to which queue? So whether it's the job queue, the device queue, ready queue, or some other queue which is not mentioned in the options. Any guesses which is the correct option? If you see, like the kernel would be maintaining uh, which state each process is in, right? And based on that state, there will be multiple queues that the kernel would be maintaining. So say this Q1 would have all the process, say like P1, P2, etc., which are all waiting to be executed, which are all, let me rephrase this, which are all ready to get executed on the process, ready to get executed. And it can maintain another queue, say Q2, which contains another set of process which are actually in the waiting state or something, waiting for some IO device. And another queue would be which are all exited properly, say P5. So these are all exited. Now the question is, which are all waiting for an IO device, right? So they are asking for this queue2. So what is this queue's name? Whether it's a job queue or a device queue or ready queue. Any option? Any guesses? Which of the following is the correct option? Option B, device queue. Okay. Any other choices? Right. So option B is the correct choice, device queue. So what are all in a waiting state for an IO device? Those should be mentioned in the device queue. The job queue as such is the wrong choice. So job queue is nothing but it will contain all the processes which are present in the memory or disk as such. So all the process, so say some process P1, it was in the waiting state for so much of time. So for better use of memory optimization, it would be swapped to the secondary storage, the disk. And later, whenever I have to use that process, I have to execute that process, it will be loaded into the main memory again. So all the processes active that is waiting to be executed or ready or in a waiting state, or some process might have exited, but its parent would still has still not accepted that child process when it's getting exited or something, or the parent is not there for the child process. Various conditions are there. So in that case, this job queue will just list all the processes which are there in memory or disk, right? This device queue will contain all the processes that are waiting for an IO device, and the ready queue would contain all the processes that are ready and are waiting to get executed on the processor. So that's the ready queue. So the correct option for this is option B, device queue. The remaining options are wrong. Any questions in any doubts in this question? Question 7. If you have, you can post it in the chat box, or you can unmute yourself and speak. So if there is no question, we'll move on to the eighth question, right? The degree of multi-programming is controlled by which one of the following? Is it a long-term scheduler or a short-term scheduler, or is it controlled by the process itself, or D, none of the above? So the degree of multi-programming is nothing but how many processes how many processes are getting executed simultaneously, all those things. So that's what is degree of multi-programming. So anyone, any guesses? Uh, this discussed in the video lectures also, whether it's option A, multi long-term scheduler. Okay, option A, we get one option from Satya Prakash. Um, right. So let's see option C. The scheduler as such is solely responsible for which process to get executed and which process should be in the waiting state and all those things, right? So the process itself cannot determine that, hey, let's just go and execute on the system. The process has no control over the system. The process is some user space entity. So say process P1, it's in the user space only. It cannot go and just go ahead and execute on the system. It has to get permission from the scheduler to execute and the scheduler is in the kernel space. Right. So option C is wrong for sure. Now we are left with option A and B or D, right? So let's see option B, short-term scheduler. So if you notice, say there are P1, P2, P3, P4, P5, five processes are there, and in your system at a time only two processes can be loaded in your main memory. So in that case, what happens is you have to decide a proper mix such that you have to select two processes out of this P1 to P5 five processes such that they are compute intensive, right? So that will be selected by the long-term scheduler. So all these processes say they have been created and they are in the disk. Now they should be loaded into the memory, and the long-term scheduler has to load this has to select any two processes, say P1 and P2, and it loads it into the memory. Now what happens is the short-term scheduler, out of process P1 and P2, it will select any one and execute on the processor. Say for 5 seconds it executes, and once that 5 seconds is over, it will switch to P2. Now, so it will alternate between P1 and P2, and say this goes on for say 10 minutes something. Now you should notice that even P3, P4 and P5 are also been waiting. So in that case, what happens every 10 minutes, the long-term scheduler would be called in. So in that case, it will notice that, okay, so P1, P2 has been executing for long. It's time to give some control to P3 and P4 also. So in that case, P1 and P2 uh, would be swapped to the disk, right? And in that place, P3, P4 would start executing. So down the line, after say 20 minutes, you will notice that all four processes P1, P2, P3, P4 would have reached some point in their execution. So all these four would not have been idle, but they would have been executed on the CPU. So this gives you the notion of multi-programming. So multiple programs, the processes are executing on the system. So the main entity that is responsible to control the number of processes that are in contention to the CPU, the processor, is the long-term scheduler. Okay, so the correct option, as Satya Prakash had mentioned, is option A. Notice the long-term scheduler would be called only few times after a large time interval, because it will take more time to execute, to choose which of the process to be loaded into the memory. The short-term scheduler would be more fast. It would be called more frequently in between, and so that the time to take the decisions by the short-term scheduler would be very low. It should be very small. The overhead should be very low. So that's why in the name itself, like the short-term scheduler, whatever processes are in the main memory are in the ready state, the short-term scheduler will see, and it will just execute, and it will give the control to one process and keep that in the running state, and then after immediately 5 seconds it will give control to another process. So that's the short-term scheduler. But there might be other processes also that are present in the secondary memory, but they don't have enough space. That's why they are just present in the disk and not got into the main memory and other conditions. So in that case, or they might be IO based also, they have just been in the waiting state and now they are ready. So in that case, the long-term scheduler has to get those into the main memory also, and give them keep them in the ready state, so that the short-term scheduler will take those and uh, get it executed by the processor. So and also the other case is the long-term scheduler has to ensure there is a good mix of both I/O as well as compute based process. So um, so all these things the long-term scheduler has to uh, do. So at one point your I/O devices should also be used properly, efficiently, not and also the CPU, the processor has also should be used efficiently. Um, the ideal case is none of the entities in your system should be idle. So the long-term scheduler has to have a good mix of the type of processes that are being loaded into the memory and placed in the ready state and all these things. So the degree of multi-programming as such should be controlled by the long-term scheduler. Okay. Any questions? Any doubts in this question? If not, we will move on to the ninth question. Sorry, we are 8 minutes uh, after the 7 p.m. deadline. I'll just wrap the last two questions in another 5 minutes. Right? Sorry for the delay. Question 9. I/O bound process spends more time doing I/O than computation with dash CPU burst, and while the CPU bound process spends more time doing computation with dash CPU burst. So it's a fill in the blank. Whether it's the I/O bound process has many short CPU bursts, or the CPU bound process has few very long CPU bursts. So any guesses which one of the following combination is the correct answer? So if you notice in the question itself, there are two process types they have mentioned. One is IO bound and the other is CPU bound. Going by the name itself, an IO bound process is nothing but much say I read one integer. I read like say multiple integers, scan of say some thousand integers. I should keep on reading from my keyboard, and then what it will do, it will just check whether the first integer is even or not, even or odd. So this even or odd will just like say I percentage 2 equal to 0, something like that. Say this is told in an array all these thousand integers, and a of 0, a of 0 percentage 2 equal to 0. So it just returns back a value telling whether the first integer is even or odd. So in that case, the time spent to get these thousand integers is very long, but the actual compute phase, which is the instructions that has to be executed, those it's just very small, just an even or odd. It will hardly contain 5 to 10 instructions as such, that which has to be directly executed. So this is what IO based IO bound process is all about, right? A CPU bound process take the opposite. You scan say some integer, some value I, some integer value I, and now based on this I value, you should find the ith Fibonacci number. So you write a for loop, and the ith Fibonacci number you should find. So assume like this I is say 10,000 or something, right? So what will happen? This for loop will run for 10,000 times, and the 10,000 Fibonacci number should be computed, right? So in that case, if you notice, just reading one integer is short. It's the time taken in the waiting state, the process would be is very short, but uh, iterating this for loop for 10,000 times is more number of instructions are getting executed. So the actual time the CPU is being used is somewhat long compared to the IO usage. So in this case, this is a CPU bound process. Okay. So out of the four options, if you notice an IO bound process, it spends more time doing IO, and the CPU time would be short. Okay. So this is short, while the CPU bound process spends more time doing computation with long CPU burst. So it takes much longer time, the CPU bound process, and IO bound process will take a shorter time. So out of the four options, you will notice that option C is the correct answer. IO bound process takes many short CPU bursts, whereas the CPU bound process takes a few very long CPU bursts. So this is the correct option, and you may notice why it's like many short and few very and like these very long CPU bursts are few. So it's just like the way programmers develop code and they write their programs. So in this case, if you notice, like say this same Fibonacci program, say this is being some user interactive program, and each time the user has to enter some number which has to get the height Fibonacci number. So this will all be executed multiple times. So this whole thing would be like a long CPU burst, is 10,000 times all those things. Whereas in the IO bound process, it is finding the even or odd after every 1,000 integers that you are scanning just for that first integer or something. This is like very short CPU burst, and usually the way programs are designed is in this follows. So the main thing is IO bound process is like short CPU burst, and CPU bound process would be having long CPU burst. That's the main point to note. So option C is the correct option. The other options are wrong, right? Any doubts in this question? Question 9. Right. If not, we will move to the 10th question, the final question. Consider the following process tree. The process ID equal the process having the process ID 8415. Let me just highlight this. Right. So it's the login process. The process ID having the 8415 process ID will wait for which of the following processes to terminate. So they have given a list of options. So the question is asking for you have a process tree. A process tree is nothing but, say you are having some process P1, okay, and this process P1 within the main function you are having some fork system call, right? You are having some fork system call, and then you will be waiting for the child to uh, based on the condition you will just wait. So based on like PID greater than 0 like that, you will be in a wait condition, and once the child gets exited or something, it will come to the parent process. So this P1 process will be the parent, and on reaching that fork system call, based on the number of these four functions are present in the code, there might be the same fork function will be invoked 10 times. So in that case, this P1 is the parent, and multiple child processes would be created, P2, P3, like that till P11 for 10 times. 10 child processes should be created. And now the P1 process, what it can do is, until all the processes finish execution, it can wait till all the children processes finishes execution. So it can use the wait system call. So in that case, The process tree denotes the parent-child relationship between the process. Now the question is, based on this process tree given to you, the process 8415 would wait for which of the following process? Whether it's PID 8416, or whether it will wait for this one, or whether it will wait for 9266. That was 92. Okay. So whether it will wait for this one, or whether it will wait for this two, or whether it will wait for this process, or whether it will wait for this whole three processes together. So I have got someone saying that it's 8416. It's nothing but bash. Okay. So this in the process tree, notice that it is usually like so. In it, say this is the parent and this is the child, right? And for the login if it's the parent, then bash distinct is the child. And for this process over here, right? So for this process over here, I will use some other thing. For this process over here, if this is the parent, these two are the child. Okay. So for each thing, the notion of parent and child would be changing. That's one point to note. Now, so we have got two choices. So same person had answered. So the first thing here, the choice was given as option A 8416. So definitely for 8415 process, so distinct, this is the parent and this is a child bash. So definitely the login process would wait for this process. So 8416 is one process, child process, and this is correct. But notice that this children are this bash process 8416 has two children. One is 9268 and the other is 9204. So if this bash process also has a wait system called somewhere within it, the process ID what 8416, this bash, even if this has a wait system called, right, this bash won't execute, it will still remain in the waiting state until the process IDs, process with IDs 9268 or 9204 will exit, right? So only when these two processes exit, the bash system, the bash process would, would would continue execution and it will stop. It will return, and only then it will exit, and then only this login process, the actual 8415, the process with 8415 process ID login process can exit. So login has to wait for this one and this will be waiting for these two. So finally, if you notice, this login will be waiting for all the three processes together. Without these two, bash won't stop. So the login process has to wait for all these three. So as we had mentioned, the correct option is option D. Uh, the login process has to wait for all these three processes. So this is the correct option. The remaining options are wrong. And PID equal to 1 is absolutely wrong because 8415 is the child of PID 1. So any doubts in this question? If, if there are no doubts, then yes, just one quick correction. So not correction, just a point to add. This long-term scheduler, so the degree of multi-programming is an important concept. So I recommend you to go through the lecture and understand this. So this long-term scheduler will control the processes that are residing in your main memory, and all the scheduling information, etc., which would take a lot of time to compute, right? To decide all those logics would be encoded in your long-term scheduler. The short-term scheduler should be very simple, and it won't do much time in it won't take much time in picking up which process to execute on the processor. The long-term scheduler has to ensure that the list of processes that are available to the short-term scheduler is given in such a way that all processes that are residing in your disk and main memory also has equal is getting equal contention to the processor for execution. So that's what the long-term scheduler has to do. And also notice that just some processes would be IO bound, some would be CPU bound. In that case, the long-term scheduler has to identify which of the processes are IO bound or CPU bound, and give, say your CPU is very busy in some point of time. In that case, it can just load an IO bound process and keep it in memory, because anyway getting a CPU bound process is of no use. So all these things it should find out. It should classify whether it's IO bound or CPU bound, and when the CPU is free, it should give preference to the CPU bound process, right? And the IO bound process, if it's just having a short CPU burst, we have seen in the next question, like IO bound processes have very few short CPU bursts. So in that case, an IO bound process, if it has to execute some instructions, say you have like process P1 and process P2, and process P2 is CPU bound and process P1 is IO bound, and the signal has got back the input process P1, it has to execute just some 10 instructions, but this P2 is keep on executing for some 10 minutes since it's CPU bound. But process P1 is IO bound, it has just some, say like 5 instructions to execute. So it's up to the scheduler to identify that just 5 instructions. I can very well stop P2, execute these 5 instructions, and say again there is some IO operation that has to take place. IO operation that has to take place for this P1 process. So in that case, it can very well stop to P2 and give control to P1. And then once its 5 instructions are over, it can then place this P1 in waiting state and again give back control to P2. So all this scheduling information has to be taken by the scheduler, and this is only for two processes. In your system, you will have your browser, and within the browser you can have multiple tabs also, and each tab can be associated with a process. It depends on how your browser uh, is configured, and also you will have your note editor, you will have some music system going on. All these things would be multiple processes, and each thing would be an IPU bound or sorry, IO bound or CPU bound, right? So based on these things, all the long-term scheduler plays an important role, right? So this one extra point that I wanted to add for this question. In that case, the 10 questions we have discussed. Any doubts in any of the questions? This session is recorded for those who joined late or those who missed some portions due to some reason. So this session is recorded. We will be uploading it on YouTube also, and the slides should also be uploaded. You can look in the course, the problem solving sessions tab in the course web page in the NPTEL site, and the links will be provided, right? So yeah, any doubts, any concepts that I should clarify? Okay. I assume you have understood the questions. You have got, you get to understand how the schedulers work and all those things. So make use of these questions, like see how we have approached, understand that. In the same way, you can try answering the week 3 sessions, the current assignments for week 3 which have been released. You can answer those and submit, right? Uh, yeah. In that case, thank you so much for attending the session, and thank you for being interactive as much as possible. Thank you, Satya Prakash. Thank you. Thank you, everyone.